Now that we know what an MMSC estimator is, how it can be derived and how it can be interpreted, we will analyze its performance. And before that, we should recall a few facts from probability theory. So to that end, suppose that x and y are two random vectors with joint distribution p of x comma y, and let us reflect about what an expectation of a function that depends on only one of those vectors represents. So as per our notation, whenever we write an expectation without any subscript, this means that we are actually computing an expectation over all random variables. Okay, so in this case it is as writing x and y here. And by the definition of the expectation, it can be expressed in integral form in this way. Now one can just rearrange terms here and note that this is the integral of f of x times this inner integral. This is just the integral of a joint PDF with respect to one of the random vectors that gives, of course, the marginal PDF of x, as we have written here. And this is nothing but the expectation of f of x just averaging over x. Okay, so we see that whenever we take expectations with respect to multiple variables of a function, then this is the same as just taking expectations over the variables that function depends on. And what happens if the function does depend on both variables? Well, in that case, the expectation can be written again as this double integral, but we can no longer do the same trick as here, right? Because f of xy depends on y, right? And therefore it cannot come out of this inner integral. What we can do here is to write this joint PDF as the product of this conditional PDF and this marginal PDF. Okay, and again, rearranging terms, we have to integrate this inner integral times p of y. And it is now easy to recognize that this inner integral is nothing but the conditional expectation of f of xy given y, right? And what we have here written in blue is just the expectation of the inner integral with respect to y, right? So averaged over y, right? So therefore we find that the expectation of some of this function equals the expectation over y of the conditional expectation over x given y, right? And this is a general fact for expectations that is often very useful in our derivations. Actually, this is precisely the same as we applied in the first example of this lecture, where we computed the expectation of the number on the ball drawn from one out of two boxes chosen with specific probabilities, right? So this is the continuous counterpart of the expressions that we derived there that were for discrete random variables. To characterize the performance of the MMSC estimator, we would like to obtain the first and second order moments of the error vector, which is defined as the true parameter minus its estimate. The mean is therefore the mean of theta minus theta hat MMSC, and this is obviously the mean of theta minus the mean of theta hat MMSC. Therefore, we need to compute this mean here, and so we just note that mean, whenever we don't have subscripts, is the mean with respect to all random variables involved, which in this case are x and theta, right? And therefore, we have the expectation of something that depends on x but doesn't depend on theta, right? And therefore, we can apply the first fact that we saw here just to conclude that this equals the expectation over x only. And now we can remember that the MMSC estimator is just the conditional mean, right? Or the mean of the posterior. And therefore, we arrive at this expression here. And just finally applying this property, it yields that this expectation here is just equal to the expectation of theta. Therefore, if we just substitute it here, we find that this is expectation of theta minus the expectation of theta, right? And that is 0. Therefore, the MMSC estimator is unbiased, okay? Now let us look at the second order moments, and let us start by the easiest part. Suppose that we have only one parameter, therefore the vector theta just boils down to a scalar. The variance of the MMSC estimator is, by the definition of variance, the expectation of the square difference of the estimator minus its mean, okay? And the estimator is, as we know, just the conditional mean, and this is, by what we saw in the previous slide, the mean of theta, okay? So this note that this is a random variable because it depends on x, right? And here what we are effectively doing is averaging the square distance between the mean of the parameter before our state of knowledge, before we see the data, right? And what happens after we see the data, where the mean of theta goes, informally speaking, right? So this is very intuitive, right? If this deviation is small, we expect low variability in our estimate. And now let us look at the more general case where m can be greater than 1. In this case, we need to look at the covariance of the error, right? So by the definition of covariance, this is the expectation of this vector times its transpose, right? And by what we saw in the previous slide, the mean of the error is 0, right? And therefore, this becomes the expectation of this outer product of epsilon and its transpose. So just by the definition of the error, we arrive at this expression, and by the second fact from the previous slide, and this expectation with respect to both x and theta can be written as the expectation over x of this conditional expectation given x, right? And now, just by substituting what this MMSC estimator is, right? This is the conditional mean, right? We find this nested expectations here, but we can note that the inner expectation is nothing but the conditional covariance of theta given x, right? Because it's the covariance taken with respect to the conditional distribution, right? So actually the posterior distribution in this case. And this is averaged over x, right? So this is, this is the variability of theta, right, for each fixed x, and then this is the result of averaging that variability across x. So again, it makes sense. The BMSC is, remember, the expectation of the square norm of epsilon, right? And therefore it is given by this expectation, and by the properties of the trace and the Euclidean norm, right? This Euclidean norm can be written as the trace of the vector inside times its transpose, right? So this is a column and this is a row, right? So therefore this product is a matrix, and the trace just adds the entries on the diagonal. Now one can note that the expectation and the trace commute, right? And that leaves us with the trace of this expectation here, which is precisely the same expectation that we had here. Therefore, this is the BMSC is just the trace of the covariance of the error, which is exactly the same as it occurred in classical estimation before we delved into the all this Bayesian business. Now we have a good understanding of what an MMSC estimator is, how it can be interpreted, how it can be derived, and how we can characterize its performance. So it is a natural next step to look into some of the special cases that typically arise in practice. And to that end, we need to learn a little bit more about the Gaussian distribution. So let us look at the bivariate Gaussian distribution. So we have two random variables that are jointly Gaussian. Its PDF is given by this expression, as we know, where the mean is a 2 by 1 vector, and C is the covariance is 2 by 2. Okay, so we will use this notation to refer to the variance of x, the variance of y, and the covariance of x and y. Pictorially, it looks like a Gaussian bell, or it is a Gaussian bell centered at the mean vector, and whose shape is determined by the covariance matrix. We see more on this later. One of the very nice properties of Gaussian distributions is that the marginals and the conditionals are also Gaussian, right? So the so P of x is Gaussian, and P of x given y is Gaussian in the same way as P of y and P of y given x, right? And I leave it as an exercise to show it. The techniques to prove this is, they are just the same as what we did in the example where we derived the MMSC estimator of the DC level in Gaussian noise, right? We express the posterior distribution as an exponential of a quadratic function, and then we identified the terms so that it could be written as a Gaussian PDF, right? But at this point, I would like just to look into the intuition and visualize what posterior or what a conditional PDF is. We have a good understanding of it for discrete random variables, and just by using the example of the balls and the boxes that we presented at the beginning of this lecture. But visualizing a conditional PDF for continuous random variables may be a little bit less straightforward. Okay, so to that end, let us just rewrite this conditional PDF in this way. Okay. And we can now just look at the numerator and note that this is a function of y when we fix x to be to take this specific value x0, right? So this amounts to just slicing this Gaussian bell along this plane where x equals x0, right? And the intersection of that plane and this two-dimensional Gaussian bell will yield the numerator in this expression, right? The denominator is just the marginal of x evaluated at x0, and therefore it can be written as the integral of the joint between x and y, right? So we observe that this denominator is nothing but the integral of the numerator, right? So again, it's the constant that we need to put here so that the resulting expression integrates to 1, right? So the effect of this of scaling by this constant is that this red curve, right, and becomes scaled so that the area underneath equals 1, right? So now we can observe here the posterior or the conditional PDF, right? And actually one can mentally move this plane back and forth along this axis and see how this conditional PDF behaves, okay? And also one of the nice properties is that we can obtain the conditional PDF without actually doing much math. One can just apply the following theorem. So if x and y are distributed in this way, just I wrote this distribution again for completeness, then y given x is Gaussian distributed with this mean and this variance, right? Where this mean is given by this expression, and the variance is given, or the conditional variance is given by this other expression, right? So whenever we need to compute a conditional PDF that involves jointly Gaussian random variables, we don't need to do the derivations that we did in our DC level estimation example, right? We did that just for illustrating this this technique of working with exponents and quadratic functions, identifying the coefficients of the polynomials, which I think is a very useful set of techniques. But we don't need to do that in practice. We just can come here and apply this theorem, and that will give us the conditional distribution. Okay, and these expressions are especially important because note that this mu of mu sub y given x is precisely the MMSC estimator of y given x, right? So this means that whenever one knows the correlation of between two random variables and also one of them, then one can do possibly a pretty good job in guessing what the value of the other variable, right? So imagine, for instance, that x is the weight of a human and y is the height of a human, right? And we know the correlation or the covariance between these two quantities, and also, of course, the other moments. Then, if somebody gives us the weight of a person, we can try to estimate the height of that person, or vice versa. So this is more powerful than actually Mason. The expressions provided by the theorem in the previous slide are actually very important. They show up over and over in estimation theory, so in many books and papers. And therefore, it is worth spending a couple of minutes interpreting them to see what is actually going on here. And to that end, let us have a look at the PDF from above. These ellipses are the contour lines or equicost lines of the PDF. This means that the value of the PDF is the same at all points of each of these ellipses, okay? The maximum is, as we said, in the point mu x, mu y, right? And it can be easily shown that the major and minor axes of these ellipses are given by the eigenvectors of the covariance matrix C. I leave it as an exercise here. You can just try to or just start from diagonalization, an eigenvalue decomposition of C to that end. And for convenience, let us recall what the Pearson correlation coefficient is. This correlation coefficient is defined as the covariance divided by the product of the standard deviations. And at this point, you may want to stop the video and try to show that this coefficient is always between -1 and 1. Okay, this is a very useful exercise of probability theory. And as a hint, you may use the fact that covariance matrices are always positive semi-definite, right? Okay, the solution is not difficult. If a matrix is positive semi-definite, then, as we know from linear algebra, its determinant must be non-negative, okay? And the determinant is given by this expression, so we just need to solve for xy, which results in this inequality, which establishes that this rho xy is always in this interval, okay? Now let us look at the expression for the posterior variance, okay? And to that end, let us multiply and divide this second term by sigma y square, okay? By doing so and taking sigma y square as a common factor, we can express this posterior mean as the posterior variance as the prior variance times this coefficient here that is always between 0 and 1, right? And therefore the posterior covariance, or posterior variance, is never greater than the prior variance, okay? So this means that conditioning never ever increases uncertainty, okay? So if there are two random variables and we observe one of them, that will never increase our uncertainty about the other random variable that we have not observed. Okay, so this is in case that the variables are correlated, right? This coefficient, this Pearson correlation coefficient, will be different from 0, right? And this 1 minus rho xy square will be strictly less than 1, right? This means that whenever there is some correlation, the posterior variance will be strictly less than the prior variance, okay? And on the other hand, if the variables are uncorrelated, right, this is 0, and then both prior and posterior variances are the same, which means that we haven't gained any information by observing x, okay? X doesn't say anything about y, and vice versa, obviously. Regarding the posterior mean, we can follow a similar procedure. We can multiply and divide this second term by sigma y in this case, and this allows us to express the posterior mean in this way, okay? One can now just look at this expression as a function of x. That would mean that this is a straight line where this is the ordinate and this is the slope, okay? So this is represented in this figure by the yellow line, okay? We see that the yellow line must necessarily go through the point mu x and mu y, and because if we just substitute here x equal to mu x, then this second term becomes 0, and then mu yx has to be equal to mu y, okay? Again, we see that if the slope, if the variables are uncorrelated, right, then this slope is 0, right? The line becomes horizontal, and therefore the posterior mean equals the prior mean, okay? So let us interpret it a little bit further. Suppose that the means are 0 and the variances are the same, just for simplicity. If in the extreme case where the Pearson correlation coefficient is -1, this is actually a degenerate case, then we can see from this expression that mu y given x is mu y plus 1 times -1 times x minus 0, right? So mu of y given x must be equal to -x. And the posterior variance that we obtain from here is 0, right? So whenever the correlation is -1, right, we recover the variable of y just by changing the sign of x, right? And that results in 0 uncertainty, right? So we are effectively obtaining one of the value of one of these random variables from the other, right? So this is, I mean, the case because this rho is -1, okay? When rho xy is 0, as we said, those variables are uncorrelated. We see that the posterior mean will be just equal to the prior mean, so in this case 0, and the posterior variance will equal the prior variance. So, I mean, we haven't learned anything. Our uncertainty has not decreased, okay? So we say that in this case x and y are, I mean, x is not informative about y, okay? And just to complete the example, suppose that the Pearson correlation coefficient equals 1, In that case, we can see that mu y given x equals x, okay, and the posterior variance is 0. Okay, so again, as in this case, we managed to obtain y deterministically from x. Okay, so this is the case, and because of this, this is the case whenever the absolute value of the Pearson correlation coefficient equals 1, right? This can be seen from this expression, right? Because then the second coefficient will be 0. Okay. And to wrap it up, let us do an exercise of 3D visualization. So we will make 2 observations and then we will combine them. The first observation is that if we slice the joint PDF along a direction that is parallel to this minor axis, right? So for instance, in this way, what we obtain is a Gaussian belt, right, in one dimension. The maximum of that Gaussian belt must be necessarily on this blue line that represents the major axis. Okay, so this was the first observation. The second observation is that the posterior mean is just the mean of the posterior PDF, right? And as we saw 2 slides ago, the posterior PDF is obtained by slicing this joint PDF along a direction that is parallel to the y-axis in this figure, right? Remember that we just take the intersection between that plane and the PDF, and then we scale that curve so that the area under the curve is 1. Okay. So the posterior mean is the mean of that Gaussian belt, right? And as we know, the mean of a Gaussian belt is precisely at the maximum. Okay. So this is the second observation. Okay, so this mu y given x is the result of cutting this PDF along a vertical direction and looking at the maximum of the resulting Gaussian belt. Okay. So now we can just plot this in 3 dimensions in our heads, right? And we will be able to conclude that this yellow line cannot go very far from the yellow line, from the blue line. Okay. The one is obtained by slicing on a vertical direction, and the other by slicing on this direction parallel to this minor axis, right? So we see that this figure agrees with that intuition. Both lines go close to each other. Okay. And note that if we change the sign of the Pearson correlation coefficient, the roles of the major and minor axes are interchanged, right? So this one now becomes the minor axis, but the posterior mean will still go closely to the major axis, right? So it will, in general, go close to the dominating axis. Okay, so and in this case, it is in these 2 cases, it is there is a clear winner, right? There's one axis that is significantly stronger than the other, right? However, we can see that in other situations where, for instance, the where the variance is not very of x and y are not very different, or the rho is not very large in absolute value. In those cases, the eccentricity is small, right? It means that the ellipses look more like circles, right? So in those cases, there is no the winner is not as there's not a clear winner, right? So both axes may be similarly important, right? And in that case, the posterior mean will lay somewhere in between both axes. Okay. And these three figures were plotted where the variance of x and y are the same. If they are different, similar observations apply. I actually left a MATLAB file on the same folder as the slides. You can use that file to make these kind of plots. So to see how these parameters affect the direction of the posterior mean. Now that we are comfortable with two jointly Gaussian random variables, we can move on to the more general case with an arbitrary number of jointly Gaussian random variables. In this context, we will often use block notation to refer to parts of vectors and matrices, right? So, for example, consider a random vector that is formed by stacking these two random vectors, okay? So remember that throughout the course, a lowercase letter with an underscore represents a column vector, right? And therefore, this is a column vector, okay? Its covariance, by the definition of covariance, is given by the expectation of this column vector times this row vector, okay? And just by multiplying these two vectors and bringing the expectation inside, we find that this covariance matrix can be expressed in terms of its constituent blocks in this way. Where now we can identify that the top left block is just the covariance of x. This top right block is the covariance of x and y, and so on. Okay. As a very simple exercise, you may try to say what are the sizes of these four matrices when x is of dimension nx and y is of dimension ny. Okay, so I hope that you made it. Cxx is obviously nx by nx, cyx is ny by nx, cxy is nx by ny, and cyy is ny by ny, right? So putting all of them together, we get a matrix that is nx plus ny by nx plus ny. Okay? Now let us extend the theorem that we presented earlier to this multivariate Gaussian distribution case. So suppose that a random vector defined in terms of these two blocks has a multivariate Gaussian distribution with this mean and covariance matrix. In that case, it can be shown that the conditional distribution of y given x is Gaussian with a mean and a covariance matrix that are given by these two expressions, right? They clearly generalize the expressions that we saw for bivariate Gaussian distributions, right? And they are expressions that show up so frequently in the rest of the course that I recommend that we all try to remember them and learn them by heart. That will be extremely useful. It's actually not difficult to remember them. The posterior mean is just the prior mean plus this correction, okay? And this correction is this term that depends on the covariances times the x minus its mean, right? So this is just x normalized to have a zero mean, okay? And this shouldn't be difficult to remember, at least visually. We have y, x, 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 right? So our retina can hold this information, okay? And the posterior covariance is just the prior covariance minus this term, okay? So remember that this is a minus, right? Remember from a couple of slides ago that conditioning decreases in principle the uncertainty, right? So reduces the variance, in this case the covariance, right? So it wouldn't make sense to have here a plus, because that would imply that our posterior covariance can be greater in some sense than the prior covariance, right? And it is also a good trick to remember these expressions, to think of the dimensions and check that the dimensions agree, right? Or check the units also, right? So for the units, you can think, for example, that y is measured in liters and x is measured in meters, for example, right? So the mean of y given x must have units of liters, right? Mu of y has obviously units of liters. When it comes to c of yx, this has units of liters times meters, okay? And cxx has units of meters square, okay? And this has also dimensions, so units of meters, right? So we have meters divided by meters square and multiplied by liters times meters, right? So those the meters in the numerator cancel the meters in the denominator, and we have that this term has units of liters. So we can add it actually to this one, right? Liters plus liters, and we get liters, okay? So this is a simple check just to make sure that the expression that you have written is correct, okay? It's very, very useful. And the same holds here, right? So this would be liters times meters divided by meters square times meters times liters, okay? So the result will be liters square, so in the same way as this as liters square, so everything makes sense, okay? And just for those of you familiar with Schur complements in linear algebra, this posterior covariance is precisely the Schur complement of this block in the covariance matrix, right? Those of you that are not familiar with Schur complements may just disregard this, because it is not necessary to follow the rest of the course, but of course it helps remembering this expression. And just to finish this slide, note that if this theorem provides the posterior PDF or distribution of y given x. If one was interested in the distribution of x given y, then one can just apply this theorem just by exchanging the blocks, right? So in this sense, note that the covariance of this vector, right, can be written in this way just by relying on the same argument here. So it is the same, same expressions can be applied without any difficulty. So just to conclude this lecture, we will apply what we have learned to the Bayesian version of the Gaussian linear model that we studied in previous lectures. So here the data is, as always, a linear function of the parameters to be estimated plus noise, where the noise is Gaussian distributed with zero mean and covariance matrix CW. Note that I lightened here the notation. Instead of writing CWW, I just write W, okay? And unlike the Gaussian linear model that we considered before, now we introduce a prior distribution for theta, okay? In this case, we will assume that it is Gaussian distributed with mean mu theta and covariance theta. So we are interested in obtaining the MMSC estimator of theta given the data and knowing all this matrix, and this matrix is here, and also this mean vector, okay? And there are two ways to solve this, accomplish this task. One is to proceed in the same way as we did in our example of DC level estimation. We can just find the posterior PDF by multiplying the likelihood and the prior, right? And then working with the exponents of the resulting Gaussian PDFs, and at some point we would be able to find the mean of this distribution here. However, it is easier if we note that x and theta are jointly Gaussian, and then we apply the theorem from the previous slide, okay? So to see that these two random vectors are jointly Gaussian, we can just note that by these assumptions here, the joint distribution of theta and W is Gaussian with this mean and this covariance matrix, right? So note the zeros here that follow from the independence assumption, okay? And one can note that the vector formed by x and theta can be obtained by multiplying this random vector here by this matrix, okay? And since a linear function of a Gaussian vector is also a Gaussian vector, then it follows that x and theta are jointly Gaussian. So to find the joint distribution, as we know, we just need to find the mean and the covariance of this vector, okay? So to that end, we just need to apply the expressions that we know for expectations that we learned in probability theory. the expectation of this vector is nothing but this matrix times the expectation of this vector, right? So it can be written in this way, and now just by substituting this expectation with its value, we arrive at this expression, and just by multiplying these two, this matrix and this vector, we obtain the desired mean. Okay. Similarly, the covariance of this vector is this matrix times the covariance of this vector times the transpose of this matrix, right? We also learned that in probability theory. If you have difficulties with these concepts, you can watch again the review video on probability theory. And multiplying these three matrices, we can write the covariance of x and theta in this way. I leave it as a simple exercise just to check that this computation is correct. So now that we have the mean of the joint distribution and also its covariance, we can apply the theorem that we saw a couple of slides earlier. Note that this top left block is nothing but the covariance of x. This bottom left block is the covariance of theta and x, and so on. Okay. So, as we know, the MMSC estimator is the conditional mean of theta given x, and by the expression that we now know by heart, this is the prior mean plus this correction here. So we just need to use this expression here. C of theta x is just C theta H transpose. C xx is just this block here, and so on. Mu x is this block here. And that gives us the MMSC estimator. For the posterior covariance, we also know by heart its expression given by the theorem that we mentioned earlier. And again, substituting the values of these covariances, we find its expression. Okay. Remember that the covariance of the error is just the expectation of this over x, but this doesn't depend on x, and therefore this is also the covariance of the error. Okay. It is, although this we can use these expressions, it is instructive to rewrite this one to interpret it further. So to that end, we can apply the so-called matrix inversion lemma, which is a well-known identity in linear algebra. It's also called Woodbury identity. You can just Google it. There is a homework exercise where you will have to derive this lemma. Okay, so the point is that we can just use it here to obtain to write this expression in this equivalent way. And this is now useful because we can think, for instance, that what happens if our prior knowledge is very weak, right? We know very little about theta, right? In that case, this covariance matrix will be large, right? In some informal sense here, and therefore its inverse would be small. Okay. So that if we remember the expression that we found earlier in this course for the MVU estimator of theta in the Gaussian linear model, that expression was precisely this, except for this c theta, which was not showing up there, right? So this means that as our prior data, prior information becomes more uncertain, the MMSC estimator will approach the MVU estimator, right? So then all the pieces in the puzzle fit together, right? This MMSC estimator essentially generalizes or extends the MVU estimator to accommodate prior information. So, I mean, we start appreciating the value of Bayesian estimation, right? And note as well that in the past we required that the parameters were identifiable. We said that this that is required that the columns of H were linearly independent, right? And that was required in order for this matrix to be invertible, right? However, now, since we are adding this covariance matrix here, this the sum of these two matrices is will always be invertible, right? So because precisely this is invertible, right? So the eigenvalues are all positive, in other words, right? And therefore we can go ahead and find an MMSC estimator. Estimate, when even when the columns of H are not linearly independent. Okay, so that is a further advantage of MMSC estimators, right? So the point is that in the past we couldn't sidestep this this identifiability issue because we didn't have prior knowledge about theta, right? But now that we have it, right, this prior information sort of solves our questions about what theta can be, right, in an informal way. All right, so I guess that at this point we are all amazed at how much we have learned today. I guess we have a much deeper understanding of estimation theory after this introduction to Bayesian estimation. Remember that the key here was to model the parameters to be estimated as random vectors, okay, and capture the information that we have about them a priori by means of a prior distribution. Okay, so this was the key novelty, let's say, of Bayesian estimation. We distinguish between information a priori, right, before seeing the data. This is captured by the prior distribution, and information a posteriori, that is information after we have seen the data, and this was embodied in the posterior distribution. Okay. It is very important to remember the terminology. This distribution was called the prior, this one was the likelihood, and this one is the posterior, okay? And note as well that the posterior is proportional to the likelihood times the prior, right? So this is sort of the golden expression that we must know whenever doing Bayesian estimation, okay? And we started by saying that the MSC that we had before didn't qualify as a suitable performance metric for Bayesian estimation. So we had to introduce a new metric that we call the BMSC, Bayesian mean square error. Right? It is defined as this expectation over both the data and the parameters, as opposed to the MSC in classical estimation, which was the average only over X. Okay. And we also showed that showed the relation between the BMSC and the classical MSC, right? The BMSC is this weighted integral of the MSC, right? So this is where we said that the prior distribution in some way it conveys information about the relevance of each value of the parameters, okay? We derived the MMSC estimator as the estimator that minimizes the BMSC, okay? And we showed that it is nothing but the conditional mean of theta given X, okay? Then we derived and extensively interpreted the MMSC estimator in many cases of practical relevance, including a lot of insight into multivariate Gaussian distributions. What remains is to look into alternative estimation criteria, right? Because the MSC has, or BMSC has certain limitations. In particular, it doesn't really account for the fact that these certain errors may be more costly than others, and this metric doesn't really care about in which direction this error is pointing, right? And another thing that we will need to discuss is how to deal with the fact that that computing this estimation may be too costly, right? I mean, this expectation may be too costly, right? So in particular, this is an expectation, and therefore it requires, in general, multidimensional integration. And we know that integrals in several variables are typically very costly, right, in a computational sense. So I will not answer these questions today, as always. I leave the suspense for the next lectures. Thank you very much for your attention.